All right, future programmers and tech wizards, listen up. If you're gearing up for your IGCSE computer science exam, you know that getting inside a computer's head is a huge deal. So today, we're going to pull back the curtain on the language that all digital devices speak, number systems. Stick with me, and by the end of this, you'll be converting binary like it's second nature.
So it all kind of starts with this one big question, right? We humans, we've got 10 fingers, so our base 10 system, what we call Denary, makes total sense. But computers, they don't have fingers. So what on earth do they use to count? And the answer? It's electricity. I mean, think about it. At the most basic fundamental level, a circuit is either on or it's off. There's no middle ground, no kinda on. And that simple two-state reality is the perfect foundation for the binary system, a whole language built on just two digits, 0 for off and 1 for on. And that right there is the key concept you've got to grasp. A 1 means an electrical switch is on, current is flowing. A 0 means that switch is off. It sounds almost too simple, right? But believe it or not, every single thing your computer does, from loading up this very explainer to catching your every keystroke, it's all just a mind-blowingly complex sequence of these on and off signals.
Okay, so here's our game plan for today. First, we'll lock down why computers are all about binary. Then we'll get our hands dirty, translating that computer speak into our numbers and back again. After that, we'll meet its cool cousin, hexadecimal, which is basically a cheat code for binary. And finally, we'll check out where hexadecimal is hiding in plain sight in the real world.
Right, let's dive into section 1. So how does a computer actually use these simple on and off switches to represent numbers bigger than 1? I mean, how do you get to, say, the number 100 with just zeros and ones? Well, it's all about a system of place values. You know how in our Denary system we have the ones column, the tens column, the hundreds column? It's the same idea. But in binary, instead of powers of 10, everything is based on powers of 2. We usually work with a group of 8 bits, which we call a byte. And as you can see here, moving from right to left, each spot just doubles in value, starting from 1. So it goes 1, 2, 4, 8, and so on. Okay, now that we've got the place values down, let's start translating. This is a huge skill for your exam, but the good news is it's really just a bit of simple addition. Let's walk through it.
So we're going to tackle this binary number together, 0111001. Yeah, it might look like something out of the Matrix, but I promise, we just need to use those place values we just talked about. The process is always the same. First, you just line up your binary number under those headings, 128, 64, 32, all the way down to 1. Now for the easy part. You just look for every column that has a 1 in it, an on switch, and you add up the number at the top of that column. So in our case, we've got a 1 under 64, 32, 16, 8, and 1. So we just add them up. 64 plus 32 plus 16 plus 8 plus 1. You add all those up, and what do you get? 121 in our good old Denary system. See? Not so scary. It's all about just seeing which switches are flipped on. Okay, cool. So what about going the other way? How do we translate our numbers into computer speak? Let's take the Denary number 142. Again, don't sweat it. There's a really clear method for this. For this, we use something called the successive division method. It sounds fancy, but it's not. You take your number, 142, and you just keep dividing it by 2, over and over again. Every time you divide, you jot down the remainder, and it's always going to be either a 0 or a 1. You just keep going until the result of your division hits 0. Now listen up, because this is the step where so many people go wrong. Seriously. Once you have that list of remainders, you do not read them from the top down. To get the right binary number, you must read the remainders from the bottom all the way to the top. And if you do that correctly for the number 142, reading from the bottom up, you get this 8-bit binary number 1001110. And that, my friends, is how a computer would actually store the number 142. Now, you can probably imagine that typing out these super long strings of ones and zeros would get really old really fast, especially for programmers. It's just asking for a typo. So they came up with a really clever shorthand to make their lives a whole lot easier, the hexadecimal system.
Hexadecimal, or just hex for short, is a base 16 system. So to get 16 different symbols, it uses our normal numbers 0 through 9, and then it just borrows the letters A through F to represent the values 10 through 15. But here's the real magic, the reason it's so useful. Every single one of those hex digits corresponds perfectly to a unique group of 4 binary digits, which is also called a nibble. It's a perfect match. And because of that perfect 1 to 4 relationship, converting between binary and hex is, well, it's incredibly fast. It's a piece of cake. There's no complicated math here. It's just a direct swap, which makes it way, way easier than having to go through Denary first.
Check out how simple this is. You take your long binary number, and starting from the right-hand side, you just split it into little groups of 4. Then you take each of those 4-bit groups and just swap it for its single hex character. So 1011, that becomes B. 1111, that's F. And so on. Slap them all together, and you get BF09. Done. It's really that easy. And guess what? Going from hex back to binary is just as simple. You just do the reverse. You take each hex digit, like 4, 5, and A, and write out its 4-bit binary code. So 45A becomes 0100, 0101, 1010. It's just a beautiful, elegant way to make long binary numbers readable for humans. Okay, so why should you care? Why does any of this matter? Well, it turns out hex is everywhere in the world of computing. And for your exam, you absolutely need to know these key examples. The big ones you're going to run into are HTML color codes for websites, those media access control, or MAC addresses for your devices, computer error codes, and the modern IPv6 internet addresses. Let's zoom in on 2 of those. You've probably seen a code like FFF000 on a website before, right? That's a hex color code. It's in 3 parts. The first pair, FF, is how much red is in the color. The second pair, 00, is for green, and the third, 00, is for blue. Since FF is the highest possible value, this code is telling the computer, give me maximum red, 0 green, and 0 blue. And what about MAC addresses? Every single device that can connect to a network, your phone, your laptop, your game console, has a unique MAC address written in hex to identify it on the network. And you know when your computer crashes and throws up a wall of text with a long error code? That's often in hex. It's pointing to a very, very specific location in memory, which is a super long binary number. And it's the same deal with modern IPv6 internet addresses. They're 128 bits long. Nobody wants to write that out in binary, but in hex, it's manageable. It all comes back to one thing. It's a compact, convenient shorthand for binary. So there you have it. We've gone from the simple on-off switches of binary all the way to the human-friendly shorthand of hexadecimal. And that kind of leaves us with a cool final thought, right? If base 16 is so useful for squishing 4-bit chunks of data, what about a base 32 system, or even base 64 to handle even bigger chunks? I mean, we used letters A through F for hex. What symbols would we even use next? It's a great question that really gets to the heart of what computer science is all about. How do we find the smartest, most efficient ways to represent really complex information?